Hi, my name is Boz Rosnan, and I'd like to talk to you about application embedding, which is a language approach to declarative web programming. This is joint work with David Lawrence. So, if nothing else, I'd like you to come out of this talk with two takeaways. One is the idea that web applications are domain-specific languages, and the other is the idea that the first takeaway actually has practical implications. Let's start with the first one. So in this talk, I'm not going to talk to you about DSLs for web applications, things like client-side DSLs or server-side DSLs. So these are all very nice DSLs, but this talk is not about them. This talk is about web applications being DSLs. So if we look at the set of all computer languages, domain-specific languages are a subset. And what I'm trying to convince you is that web applications are a subset of that. So that Facebook, for example, is a special case of a domain-specific. So first, Facebook is a language, and it is domain-specific. First, I would like to try to convince you that web applications are a special case of computer languages. So, what's an application? An application is a combination of database schema, presentation, and business logic, which itself comprises of access control and the part that, with lack of better name, I will call it doing something. The part where we define what the application actually does. A language, on the other hand, is a combination of syntax, which has its abstract and concrete parts, and semantics, which has its static and dynamic parts. Now, a database schema is similar to an abstract syntax in the way in that they both define types of things. The types of things that go into the database or the type of things that go into the program. Presentation, like concrete syntax, gives human-readable forms to those things. Access control, like static semantics, restricts what can be placed in the database or in a program beyond what the schema or abstract syntax allow. And by doing something with the data, we actually give it meaning, kind of like dynamic semantics for a language. So we have compared the data in an application to a program in a language. Now, this is simply a special case of a very well-founded principle in computer science. For example, this guy made a career out of telling people that programs are data. And that guy found a way to represent numbers as functions, which is another way of saying that data is a program. So now that I may have convinced you that that web applications are languages, let's see why I say that they are domain specific. So the reason is in the schema. So what's in the schema for an application? So if it's something like Facebook, the schema will include statuses, friendships, and likes. If it's something like Twitter, we'll have tweets and followers. If it's something like eBay, we'll have products, inventory, orders, buyers, sellers, this stuff. These are all domain concepts. So if we agree that the schema is an abstract syntax, then all our language concepts are domain specific, making the language a DSL. So I hope I convinced you that web applications are DSLs. Now let's see what kind of practical implications this idea has. So first, let's talk a little bit about web applications. One thing about them is that they are everywhere. You cannot ignore them. Unfortunately, they are very hard to get right. Look at how many bad web applications you know out there and how few really good ones, and for those really good ones, how many resources were poured into them to make them that good. Now, what do I mean when I'm saying that they are complex? The word complex comes from the archaic verb to complect, to interleave or tangle. So what's tangled in a web application? One thing is functional requirements, what the application actually needs to do. Things like its schema, presentation, and business logic. The other thing is their extra functional requirements. Things like performance, scalability, availability, and more. Now, why am I saying these things are tangled? Well, take a look at how applications are designed today. If we have a small-scale application, we will probably design it using a relational database, which will be normalized with no redundancy, and we will use a high-level web framework, something like Ruby on Rails. But if we take the exact same application and just change the scale, we may end up with a totally different design. A NoSQL database, which will be heavily denormalized with a lot of redundancy that is maintained by the business logic, and the assumptions made by high-level web frameworks like Ruby on Rails no longer hold at scale, and we will end up using lower-level frameworks, things like Express.js maybe. So I want to look at this problem from a software use perspective. Let's take a look at all the software artifacts that make up a traditional web application and see how they fit into these four quadrants based on those following axes. One is application-specific artifacts versus application-agnostic artifacts. This is under the assumption that application-agnostic artifacts are not affected by any of the functional requirements for our application. And on the other axis, I would like to separate between imperative and declarative artifacts. This is under the assumption that declarative artifacts have no effect on extra functional requirements. So we will be very interested in what goes into this yellow box, because this is where potentially things are coupled with both functional and extra functional requirements. So the database that we use and the web frameworks that we use are both imperative and application agnostic. So they have a lot of effect on extra functional requirements, things like performance and scalability, but they are not built for our application, so they have no idea what the functional requirements are going to be. And therefore they can be reused across many applications. There are things like CSS frameworks that are both declarative and application agnostic, but there aren't many of those, and they're not very important for this conversation. And there are things like static HTML, CSS, or templates, if we use a declarative template language, which are application-specific but declarative. So they are coupled with the functional requirements for our application, but not with the extra functional requirements. But there is one big thing in traditional web applications that is both imperative and application-specific, and that is the business logic. And this is where functional and extra functional requirements are being tangled. What we are proposing is a different separation of code assets, where we have something we call the application platform or host application, which is imperative but application agnostic. So it is only coupled with the extra functional requirements. There is the declarative application definition, which is of course application specific, which only handles the functional requirements. And we really want the yellow box to be empty. But in fact, in real life, we cannot make it absolutely empty, so it's going to be very small. and it will only contain user actions, things that happen on the presentation side when a user does things like click a button, because this is an action that needs to be defined imperatively, but we restrict that to the presentation layer, tier only, so its effect on things like overall system performance and scalability are very limited. So our approach is called application embedding. It's defined as the implementation of an embedded application as payload or as data over a host application. And the intuition is that it is DSL embedding applied to web applications. But what does it mean? So to really explain this, I'm going to take two detours. In the first one, I'm going to talk about DSLs and how the complexity of having functional and extra functional requirements is dealt with there. So functional and extra functional requirements exist in DSLs as well. The functional requirements of a DSL are its syntax and semantics, while the extra functional requirements are things like performance and tools around the DSL, things like syntax highlighting, debuggers, etc. So how do DSL developers handle this complexity? So that depends heavily on how the DSLs are implemented. External DSLs, like HTML, CSS, and SQL, for them it's every man for himself. If you embark on the adventure of creating your own browser, implementing HTML and CSS in the process, you will be expected to provide good tools to debug HTML and CSS on your browser. Otherwise, chances are web developers will not target your browser when building their own web applications. Another approach is to use language workbenches, things like MPS, Xtext, or SpoofX. These are frameworks that allow us to build DSLs along with their tooling. So we still have to implement everything, but we're doing it from within frameworks that makes the job much easier. And a third approach is DSL embedding or internal DSLs. These are DSL embedding is the embedding of a DSL as a library over a host language. For example, if we use Racket as our host language, embedding a DSL in Racket means writing a Racket library, and the DSL code is actually Racket code. And if our DSL code is Racket code, then all the tools that exist for Racket will also help with our DSL. So if I look at the separation of code assets for an internal DSL, and for this discussion, I'll restrict the discussion to only declarative host languages, then we see something like this. The host language itself and its tools are implemented probably imperatively, but they're agnostic of our DSL. They know nothing about our DSL. Our DSL is implemented as a definition, actually, declaratively, because our host language is declarative. And the yellow box is empty, which is exactly what we want. So that brings us to the big idea of this talk. So if we agree that web applications are DSLs, and if we agree that there is a way to build DSLs that supports the kind of separation of code assets that we want, can we apply it to web applications? And the answer is yes, and it is already being done today in content management systems. So content management systems are computer applications that support the creation and modification of digital content. Examples include WordPress, Drupal, and MediaWiki, which is the software behind Wikipedia. If we look at CMSs or a website powered by a CMS, and we look at the separation of code assets there, we will see something very similar to where we are heading. The CMS implementation itself is imperative but site agnostic, so that for example, all the examples on the previous slide were implemented in PHP, which is an imperative language, but they are agnostic of any particular site that we want to build on top of them. There are things like themes and styles, which are declarative and site agnostic, again, not very interesting. The site content itself and settings, like who is allowed to do what, are both site-specific and declarative. And again, the yellow box is empty. So application embedding, so how does application embedding apply to CMS? Well, so in WordPress, the host application is WordPress itself, and the embedded application is the site or the blog that we built on top of it. It has some interesting pros, like all the extra functional requirements are handled by the CMS, so that I do exactly the same thing on my site or blog, whether it is to be viewed by one person per day or a million. It can also be provided as a service, like WordPress.com hosts WordPress. So I don't have to worry about spinning a server and connecting it to the internet. But they have a very serious con, and that's the fact that they are very limited in functionality. The business logic that they support is very minimal. So, for example, a static website has absolutely no business logic. The business logic is empty. The site is static. So, if we want to use this approach, but we want to use this approach for an arbitrary application, for a general application, what do we need? I guess we need a general purpose host application. So what is a general purpose host application? So again, let's take a look at the set of all computer languages. Again, domain-specific languages are a subset. But now we treat the set of web applications as a subset of computer languages, but not a pure subset of DSLs. So the vast majority of web applications are still domain-specific, including CMSs like WordPress, because they are specific to the domain of content management. But there is a tiny, tiny little subset of web applications that extend beyond domain-specific languages, and these are the general-purpose web applications, including one piece of related work named CouchDB and our very own fish tank. So what is fish tank? It's the proof of concept we provide as validation for our work. It's a host application, which is a platform for developing and hosting web applications. It is an implementation of the CloudLog language, since it is a language, which is a host language for applications. So what is CloudLog? It's kind of it's a logic programming data language, kind of like a Datalog. It consists of axioms, and there are three kinds of those: facts, which are data elements, rules, and clauses. Clauses are evaluated at query time, as in Prolog, and rules are evaluated at update time, kind of like in Datalog. The evaluation is through modus ponens, in other way. I'll give you a small example. So this is a Twitter-like example. So we have facts like Alice follows Bob, and like Bob tweeted hello. And there is a rule that says that if one user follows another user and the other user tweeted, then the timeline of the first user will include that tweet. We treat rules and facts as fish in a fish tank, in what we call the fish tank model, which is the computational model that evaluates CloudLog. So we treat rules as female fish and facts as male fish. Now, if the fact matches the left-hand side of a rule, they create an offspring, and that offspring in this case is by itself a rule, a female fish, matching all of Bob's tweets into Alice's timeline. Now, when that meets a fact, the Bob's tweet, they create yet another offspring, which is in this case a clause, which is infertile. It cannot have its own children, but it is visible to queries. So we can query Alice's timeline and get Bob's tweet. Now, the nice thing about the fish tank model is that the order of operations does not change the end result. For example, if Bob tweeted hello before Alice started following him, we will still get the same result at the end. Rules can come either before or after the facts that they interact with. So we can put the rule after the facts are already there, and it looks very simple here, but in traditional applications this is actually a very big problem. It's called data migration. What happens when you want to upgrade your application when you already have data in the database? And of course, removing facts or rules will have the result of removing all their descendants. So again, the order of operations of either insertion or removal doesn't matter. As architecture, we chose the mean architecture with MongoDB as our data tier, Node.js and Express.js on the logic tier, and for the presentation tier, we have an AngularJS plugin. You'll find more information about this in the paper, as well as a formal definition of the fish tank model, an evaluation in the form of a Twitter-like application, which is more elaborate, of course, than the one we saw right now, and a discussion of applicability, correctness, and performance. You'll also find a discussion of related work, including application embedding and multi-tier or tierless programming. So to conclude, I hope I convinced you today that web applications are domain-specific languages. And I hope I also convinced you that they have very serious practical implications, such as the ability to define applications declaratively, and that they provide separation of concerns between the functional requirements that can be dealt with in the application definition and the extra functional requirements dealt with by the host application. Thank you very much.